Hello, welcome to the course. In this chapter, we'll study some basics of energy. That is, where the world gets its energy from and what are the problems with it. So, the punchline is essentially today the world gets 80% of its energy from fossil fuel sources, and the use of fossil fuel sources leads to global warming. And that's one of the biggest problems facing mankind. And so that's what we're going to learn in this course, and we'll see what we can do about it. All right, so let's get started. All right, energy is a important, very important in your life. You need energy to do work, and so it's estimated that you spend $1 out of every $10 spent on energy. Okay, so that's how important energy is. So, for instance, if a nation wants to become rich, unless you have a steady, cheap source of energy supply, there's no way you're going to be rich. Okay, so energy is very important for progress. Okay, so it's an important part of our life. Now, unfortunately, the world uses, of course, we spent a lot of money on energy, and so the world uses the cheapest source of energy, not the cleanest, the cheapest source. Okay, so right now, fossil fuels are the cheapest source of energy, and that's why we use them. Okay, unfortunately, the use of fossil fuels have negative consequences. So again, the world gets 80% of its energy from fossil fuel sources. And what are the fossil fuel sources? They're coal, oil, and natural gas. And so this graph shows you that. So this is the primary global energy consumption in 2022. And it hasn't changed much in 2023. So you can see that coal is about 27%. Natural gas is about 23.5%, so 27 plus 23, that's about 50%. And then oil gets you another 32%. So in 2022, there was 82% of our energy came from fossil fuel sources. Okay, and these are renewable sources, hydroelectricity, renewables. So those are the green sources, and that's nuclear energy. Okay. Now, these sources do not dump CO2, carbon dioxide, in the atmosphere, the greenhouse gases. The use of these guys leads to increased CO2 in the atmosphere, which is a greenhouse gas. All right, and that's the rub. So we'll study issues involved in transitions to renewable energy. So what our goal is for these sources to provide 80 to 100% of the world's energy, and the use of these sources to go away. And hopefully this will happen within the next 50 years. Okay. So energy comes in various forms: chemical, radiant, and nuclear energy. Okay. So these are chemical sources of energy. Solar energy is radiant energy, and nuclear energy comes from splitting nuclei. Now, energy cannot be created or destroyed. So all we're doing is, whenever we use energy, we're using one form of energy and converting it to another, more useful form of energy. For instance, you burn oil in your car, and that energy is converted to the motion of the car. So the motion of the car is useful, and that's what you're doing. You're converting the energy content of gasoline into motion. Okay. And you learn that in your car is about 20% efficient. What that means is $100 worth of energy contained in oil is converted to $20 worth of motion in your car. Okay. We convert coal to electricity, and because electricity is easily transported across the nation and so on. Okay. So electricity is a very convenient form of energy. And we do a lot of that. We convert coal to electricity. Hopefully in the future, a lot of our electricity will be coming from wind and solar. Okay. So, in everything we do and everything that happens in nature, energy is only transformed from one form to another and transferred from one object to another. Okay. So, what that means is, let's say you push a cart, energy is transferred from you to the cart. Okay. So, however, the total energy of the universe remains constant. So, you're never creating or destroying energy, you're just converting it from one form to another and transferring it from one object to another. Okay, so you're converting energy from one form to another. So, in principle, any form of energy can be converted to any other form. Okay. And I'll show you a graph representing various technologies that we use to do that. Some form of conversions are more efficient. So, for instance, when you drive your car has kinetic energy, and that's a form of mechanical energy. So, 100% of the mechanical energy can be converted to heat. Okay. So, mechanical energy to heat, 100% of that is possible. Now, on the other hand, the opposite process, you're burning gasoline and that releases heat, and you're trying to convert that to motion, which is mechanical energy, and your car is about 20% efficient. Okay? The other 80% remains as heat and is thrown out your tailpipe. Okay? So, you see, this process is 100% efficient, but the opposite process is only 20% efficient. Okay? Now, again, this was the useful form of energy, but you couldn't convert 100% of that to that. Okay, 80% of it remained heat and was wasted. So every time you put $10 worth of gasoline in your car, you get only $2 worth of motion. You're throwing out $8 worth of energy through your tailpipe. Okay. So again, in practice, heat to mechanical conversion is only about 20 to 40% efficient. 40% is some of the highest efficiencies we've achieved. Those are the thermal power plants and so on. All right, so here's a simple device. Here's a swinging pendulum. This has potential energy here, and when it's going the fastest at the bottom, all that energy is kinetic energy, and then back to potential energy. And so as the pendulum swings, potential energy is converted to kinetic, potential, so back and forth it goes. Okay. So this shows you potential energy decreasing, kinetic energy increasing, maximum kinetic energy decreasing, and potential energy increasing. Okay. So here's a simple device showing you conversion of energy. Okay, so here is a diagram showing you various processes that can convert energy from one form to another. Okay, so for instance, plants can absorb solar energy, and via photosynthesis convert that to chemical energy. And you can eat that stored food and you oxidize it, and you can convert that to eventually to radiant energy. Okay, so photosynthesis can convert radiant energy to chemical energy. Solar cells convert radiant energy to electrical energy. Electric motors convert electrical energy to mechanical energy. Electric generators, which we'll talk about, convert mechanical energy to electrical energy. So again, these show you various kinds of devices that we use in our life. Okay, so for instance, a heat engine, your car is a heat engine, is converting the energy in the gasoline to mechanical energy. Okay, and so on. Okay. On Earth, ultimately we get all our energy from the sun. Okay, so from the sun we get, except for nuclear energy, but we'll come to that later. Okay, so from the sun you get electromagnetic energy. The plants convert that to chemical energy, and you consume the plants. You consume energy from there, and that energy, and you can use that for various activities in your life. And that energy eventually gets converted back to when you brake your bicycle. That all that energy in the motion gets converted to heat, which eventually gets converted to radiant energy, electromagnetic energy back. Okay. So all our energy sources except for nuclear energy can be traced back to the sun. Even nuclear energy can be ascribed to previous generation stars that have exploded as supernovae and seeded the clouds of subsequent generation stars. So all our nuclear energy currently comes from uranium 235, and these atoms were manufactured in exploding stars and colliding neutron stars. So all the uranium on Earth was manufactured in supernovae and colliding neutron stars. Okay, so and that's where we get our nuclear energy from. And we'll devote 2 chapters to nuclear energy. All right, now we'll spend a couple of minutes on the technical definition of work. Again, like I said, we need energy to do work. Okay. So for instance, if you push an object, so here's a fella pushing this lawnmower, he's applying a force like that, and he pushes the lawnmower through a distance d. The amount of work he does is the force that is applied times the distance the object moves times cosine of the angle between the two. Okay. So that's how you calculate the work done. And the units, the SI units for work are the joule. Force is measured in newtons, distance is measured in meters, and this is unitless. So the units of work are force times distance, Newton times meter, and that's a joule. Okay. And remember, you need energy to do work, so the units of energy are the same. So units of work and energy are joules in SI units, and that's the units we'll use. Okay. Okay. Now you just need to be aware of this. Okay. So you won't be using these formulas in problems or anything like that. Okay. So this guy, when he did work on him, he transferred, it took energy to do work, and energy was transferred from him to the object. Okay, because this was at rest and now this started moving. Okay. So we need energy to do work. When work is done on an object, it gains or loses energy. So for instance, if you do 100 joules of work is done on an object, it gains 100 joules of energy. So if you lift an object up and you do 100 joules of energy on this, you do 100 joules of work, when you lift this up, this object will have 100 joules of energy because it will have 100 joules of potential energy. Okay, and that's the idea. Now we'll briefly talk about heat engines. What heat engines do is they convert heat to other forms of energy, other useful forms of energy. For instance, your car is a heat engine. Your car burns gasoline, and from the heat released, it converts some of the heat to the motion of the car. Okay, and like we already said that your car is about 20% efficient. Okay, so a coal power plant is a heat engine. What that does, what a coal power plant does is it burns coal. From the heat released, it boils water, and from the steam produced, they use the steam in generators to produce electricity. So a coal power plant converts heat to electricity. Now a coal power plant is about 40% efficient. Okay. But anyway, and the other 60% cannot be used, and that heat is dumped out. Okay, So heat engines convert heat to other forms of energy, either kinetic energy, electricity, or whatever. Okay. So here's the general. Here's a cartoon diagram for a heat engine. So this could be a car, this could be a coal power plant, this could be a nuclear power plant. Nuclear power plant is also a heat engine. So it gets a heat engine has a hot source. So that's where you're getting the heat from. Some of that is converted to work. Okay, work being to other useful forms of energy. And the part that cannot be converted, you throw it out in the atmosphere. And that's a cold sink. Okay, so you're absorbing this much heat, you're converting part of that to work, and you're dumping out the rest. So for your instance, in your car, in your car, when you burn gasoline and let's say you release 100 joules of heat, only 20 joules is being converted to the motion of the car, and 80 joules is thrown out your tailpipe. Okay. All right, Mr. Carnot, a French engineer, answered the question, what is the maximum efficiency possible for this heat engine, for a heat engine? So he discovered the upper limit, what is the best you can do with a heat engine. And this is what Mr. Carnot found. This is the efficiency. The efficiency of an ideal heat engine just depends on the operating temperature. And these temperatures are on in the Kelvin scale. Okay, so Mr. Carnot said that, this is the maximum possible efficiency of a ideal heat engine operating between those two temperatures. So TH is the hot reservoir temperature and TC is the cold reservoir temperature. So for instance, for your car, that's the heat being dumped through the tailpipe, so the cold reservoir temperature would be the temperature of the atmosphere. Okay, and so if you look at this equation, the efficiency can be 100% if the cold reservoir was absolute zero. Okay, so if outside the temperature outside was absolute zero, and that's impossible. Okay, so this essentially says that you can never have a 100% efficient heat engine. Okay, one other scenario would be if this temperature was infinite, then you can have a 100% efficiency. But anyway, in practice, you can never have a heat engine that's 100% efficient. Okay, and as I've already said, your car is only 20% efficient. Okay. All right, now we'll see how all electricity is produced in the world today. How most of the electricity is produced in the world today. And this utilizes Faraday's laws. Okay, and so I'll show you an electric generator, a simulation for an electric generator. Okay, here are two magnetic poles. Here's the north pole of a magnet. Here's the south pole of a magnet. And here's a piece of wire. This is called an armature. And now, if you turn this wire in between these magnets, what will happen is the energy used in turning the wire gets converted to electrical energy. So if you turn this wire, what you do is you produce electricity. And with this setup, you produce an alternating current voltage, an alternating voltage. So whatever energy you put in turning this wire got converted to electrical energy. So here's a device that transforms one form of energy into electrical energy, or it transforms mechanical energy into electrical energy. You haven't created electrical energy. All you have done is, using this device, transformed mechanical energy, the energy you put in turning this wire, into electrical energy. Okay, so let's see how this thing works. I'll show you a simulation. Okay, so here we go.
What you're looking at is a very simple alternating current or AC generator, a device that converts mechanical energy into electrical energy. This part is called the armature. It's made from metal and electricity is generated by its rotation between two magnets. To show clearly how the generator works, one half has been coloured yellow. The armature can be rotated in various ways, for example using pressurized steam, as in a power plant, a flow of water from a dam, or a flow of air from a wind turbine.
So you saw that. So in practice, how do we turn that piece of wire? In a dam, flowing water turns that piece of wire. Okay. So you're converting the energy of the water, the energy stored behind the dam, into electrical energy. In a wind turbine, when the wind turns the blades of the wind turbine, that turns this piece of wire. So ultimately, your goal is to turn this wire. Okay. In a coal power plant, you burn coal, boil water, and get the steam to turn this piece of wire. In a nuclear power plant, you split nuclei, heat is generated, you boil water, and that steam produced is used to turn this wire. Okay. So again, ultimately, whatever energy you put in turning the wire gets converted to electricity. Okay. So that's how currently most of our electricity is produced. Now, solar cells work differently, and we'll talk about that in one of the later chapters. Okay. All right, and again, we produce electricity because it's very easily transported, and it's a very useful, again, because it's very easily transported. Okay, so that's one of our most useful form of energy. Okay. Now we'll define power. Power is the rate at which work is done. So you've done this much work, and this is the time you took to do the work. Okay, and smaller the time, greater the power. So faster you do a bit of work, greater the power. So the power is work done per unit time. And the units for power are watts. Okay, units for work are joules, units for time are second, and a joule per second is a watt. Okay. And a horsepower is defined as 746 watts. Okay. And this is the rate at which a horse could work for a full day for 8 hours, and so that's how the horsepower came about. Okay. All right. So the reason we introduced this is we'll come to our various power generators. So, for instance, the Hoover Dam is a typical large power generator. And the approximate power is about 1 billion watts. Okay, so 1.34 billion watts. So we'll say 1 billion watts, and that's written as a gigawatt. So here's a number you want to remember. A gigawatt is a large power plant. And you can run 1 million homes with this power plant in the US. A little less than 1 million, but we'll keep numbers approximate. Okay, so here's what you want to remember. A gigawatt is a large power plant, and with a gigawatt, you can run 1 million homes. Okay, now here are various other power consumptions. Your television is about 200 watts, and you are consuming about 100 joules of energy per second. So you're like a 100 watt bulb. Your brain, by the way, uses 20% of that energy. Okay. So again, energy is very important, as we said, and energy is a key constraint in the rapid economic growth of a nation. So if a nation wants to become rich, you had better have a cheap, steady source of energy. Okay. Now, here's the thing about fossil fuels. Okay, again, so like I said, today the world is getting 80% of its energy from fossil fuels, and 20% from renewables. Now, the problem with fossil fuels is the following. You take fossil fuels and you burn it, so you convert that to heat, and then you want, let's say you want to convert that to electricity, okay, and that process is, let's say, 30% efficient, or let's say 35% efficient, okay. So you see 65% of that heat is just thrown away. So the use of fossil fuel to electricity is very inefficient. And this is real dollars, we'll see. So this is a graph showing you the US energy consumption in 2018, but again, this hasn't changed much. Okay, so here are the primary sources. This is where we're getting our energy from. And you can see the biggest chunks are natural gas, coal, and petroleum. Okay, those are all fossil fuels. And the way to extract energy from them is you burn them, okay? And then try to convert them into either motion or electricity. And that's an inefficient process, okay? So this is where our primary source of energy comes from, okay? And so you see, all this adds up to 100 quads. A quad is roughly, one quad is roughly 10 to the power 18 joules, okay? So that's a million trillion joules, okay? So in the US, we consume 100 quads of energy annually. A quad is that, okay? So these are the energy sources, and because you burn these things, and heat is not converted to other forms of energy efficiently, you see this much, 70 quads is thrown out the window. That's just mind-boggling. 70 quads, okay? What that means is, so in 2020, the US spent $1 trillion on energy, 5% of our GDP. And so you spent $1 trillion on energy, and 700 billion was thrown out. $700 billion worth of heat was thrown out. So that's the status today. Now, if all the energy came from wind and solar, you're producing electricity, and electricity is used 100% efficiently, essentially 100% efficiently. Okay? So there wouldn't be any wasted energy. Okay? So that's why we want to, so converting to renewable sources will have many benefits. Okay, again. All right, so again, I hope you understood this point. So we spent $1 trillion on energy, and because our energy sources were mostly fossil fuel sources, $700 billion of that is the heat produced from these energy sources. $700 billion worth of heat is not usable. All right, now let's look at the world. Okay, so to run the world per year, so the world consumption, so, and this is roughly true today as well, to run the world annually, you need this much energy, 600 times 10 to the 18 joules of energy annually. And again, 80% of the energy comes from fossil fuel sources, coal, oil, and natural gas. Oil, natural gas, and coal. Okay, so bulk of the energy of the world comes from these three fossil fuel sources. Now, I'll show you a useful number to remember. Okay, so again, like I said, a 1 gigawatt plant is a large power plant. Okay, and you'll come across this number often. So nuclear power plants generally are about a gigawatt and so on. Okay, so what this shows you is, okay, so this is the energy needed to run the world annually. Okay, this is a gigawatt, so we'll divide that by a gigawatt, and that's how many seconds there are in a year. Okay, what this tells you is, it tells you about 19,000 large power plants are needed to run the world 24/7. Okay, so so that's a good number to remember. Okay, with our current mix of 80% fossil fuels and 20% renewables, you're needing between 15 and 20,000 Hoover dams to run the world 30, 24/7, 365 days. Okay, so to power the world, about 19,000 large power plants must be humming 365, 24/7, as is shown in the calculation. Okay. Okay, so what you learn is, so once we switch to renewables, once all our energy is coming from solar and wind and nuclear, so let's say 100 years in the future, we'll probably only need about 12,000 large power plants, because you're not wasting all that heat that fossil fuels do. Okay, so right now, this is how much we need with 80% fossil fuels and 20% renewables. Okay. With 100% renewable, you will probably run the world on 12,000 gigawatts. Okay, and we'll see that later on. Okay, so fossil fuels. What are the fossil fuels? Coal, oil, and natural gas. Coal, natural gas. Okay, so how do we extract energy from fossil fuels? You burn fossil fuels and you get heat, and some of that heat is converted to work. Okay, now when you burn fossil fuels, you produce carbon dioxide. Carbon dioxide is a greenhouse gas, and we'll see how that works later in the chapter. And this causes global warming. And this is one of the biggest problems facing mankind. Okay. So the use of fossil fuels is leading to global warming. And again, we'll talk more about this. Okay. So global warming is one of the biggest problems facing mankind. So the world needs to switch to renewable sources as soon as possible. So here is methane. Okay, this is methane. And this is one of the fossil fuels. This is a natural gas. This is the main component of natural gas. Okay, so when you burn natural gas, what you're doing is you're combining with oxygen. Okay, and methane, when burnt, produces carbon dioxide. This guy is the culprit. This guy is the villain, and water molecules, plus energy, plus heat. Okay, that's why you burn methane. You're after the heat, and then you use this heat to convert to electricity, motion, or whatnot. Okay, so when you burn methane, it's mostly using this heat to convert to electricity. Okay, so every time you burn fossil fuel, you're producing carbon dioxide. Okay, fossil fuels are hydrocarbons. Hydrocarbons are compounds that have hydrogen and carbon. That's why they're called that. Okay, so plastic is a long chain hydrocarbon. Here's motor oil. Here's diesel. Here's gasoline. Gasoline mostly has 8 carbon atoms, and this is called an octane molecule. 1, 2, 3, 4, 5, 6, 7. All right, so hydrocarbon with eight carbon atoms is called octane. Okay, so this particular one is heptane. But anyway, so fossil fuels are hydrocarbons. We burn fossil fuels and convert the heat generated to electricity. Okay, or mechanical energy in your car. So again, as we keep saying, unfortunately, only 1/3 of the heat is converted to electricity or mechanical energy. The rest is wasted. All right. So for fossil fuels, it turns out that what this diagram tells you is the larger the HC ratio. Okay. So natural gas, petroleum, coal. Okay. the larger the hydrogen to carbon ratio, the more the increasing energy content, increase when the HC ratio is increasing, energy content increases, and the CO2 generation decreases. So of all these guys, natural gas is the best fossil fuel source to use. Coal essentially is pure carbon, okay, and it generates the most carbon dioxide. All right, so now let's talk about the greenhouse effect, okay, and the process that makes the Earth warm, okay. So here's our Earth. We are getting energy from the sun, okay, and the energy that's coming from the sun is mostly visible electromagnetic radiation. The Earth absorbs, it turns out that we absorb about half of this radiation and the other half is reflected back and so on. We absorb about half of this radiation and then the Earth warms up and we radiate this as infrared radiation. So what we get is visible light and what we radiate back is infrared radiation, okay? Now it turns out that our atmosphere doesn't have the same properties towards visible light and infrared light. Okay, our atmosphere is essentially transparent to visible light. Okay, and depending on if you dump greenhouse gases in our atmosphere, the greenhouse gases absorb this infrared radiation. So, for instance, okay, so here's our Earth. Here's our Earth, and let's say we get visible light in. Okay, so here's our atmosphere, and if you put greenhouse gases like carbon dioxide in our atmosphere, this is visible light. Let me use a different color for incoming radiation. So here's visible light, and here's infrared radiation going out. Okay. Now, these greenhouse gases, what they do is they absorb the radiation and they emit it in every direction. Okay, so the more carbon dioxide there is in the atmosphere, it absorbs this outgoing radiation and it emits in all direction. And so some of that radiation gets trapped and it warms the Earth. Okay, so again, so let's get back to that diagram. Okay. So you're getting energy from the sun and you're getting visible light and you're radiating infrared light. Now, if you want to maintain a constant temperature on the Earth, if you get 100 units worth of energy, you want to radiate out 100 units of energy. Okay, now if you radiate less energy, then you'll warm the Earth. And that's what's been happening for roughly the last 60, 70 years. We have been radiating less energy than what's coming in. And that's warming up the Earth. Okay. Well, how much has it warmed up? So for instance, in 1850, let's say, the temperature of the Earth was 14 degrees Celsius, the average temperature. Now in 2023, okay, the temperature of the Earth has risen to 15.3 degrees Celsius, roughly. Okay, so we have warmed up the Earth quite a bit. Okay, that's because we are radiating less energy than is coming in. And why are we radiating less energy? Because we've been using fossil fuels which dump carbon dioxide in the atmosphere, which is trapping this outgoing infrared radiation. Okay, so that's the greenhouse effect. That's the greenhouse effect. So what we want to do is for the world to switch from using fossil fuels so we don't dump CO2 in the atmosphere and don't trap this infrared radiation. Okay. Our goal is to be below 16 degrees Celsius. Our goal is to be below 16 degrees Celsius. We'd love to be below 15.5 degrees Celsius, but that probably won't happen. Okay, and we'll talk about, I'll tell you why we need to be below 16 degree later in the chapter. Okay, so again, the radiation coming from the sun is mostly visible light. What we are emitting is infrared radiation. Okay, and because of the molecules, because of the greenhouse gases that we are dumping in the atmosphere, this radiation is being absorbed and being trapped. Okay, that radiation is being absorbed and trapped. Okay, so if the total energy radiated is equal to the energy arriving, equilibrium is maintained and the Earth's temperature would remain constant. On the other hand, if the total energy emitted is less than the energy arriving, the Earth will get warmer. Okay, and that's what's happening. All right, so what this diagram shows you, so here's energy coming from the sun, and the clouds reflect about 20% and so on. Ultimately, about the surface of the Earth absorbs 50%. Okay, and then this absorbed energy is radiated back as infrared radiation. All right, so the Earth is that 50% absorbed is being emitted as infrared radiation. Okay, and this carbon dioxide, like I said, is a greenhouse gas, and this carbon dioxide absorbs the infrared radiation. The carbon dioxide does not absorb the visible light, so the atmosphere is transparent to visible light, but it's not transparent to infrared light. So it absorbs infrared light and then emits in every direction, and so some of that radiation gets trapped and warms the Earth. Okay, so the infrared radiation emitted by Earth upward is absorbed by the greenhouse gases. CO2, methane, or CO2 and methane are two of the biggest greenhouse gases. CFCs are also greenhouse gases, and I'll show you a table with that. Okay, so those are the greenhouse gases that trap infrared radiation from going out to space. Okay. Of course, more CO2 there is in the atmosphere, more of the radiation would be trapped, further increasing the temperature of the Earth. So we'll see how much CO2 has increased, in the atmosphere over the years. All right. So we do need a little of CO2 in the atmosphere. So for instance, if there were no CO2 in the atmosphere, if there was zero CO2 in the atmosphere, the average temperature of the Earth would be minus 18 degrees Celsius. And that's not good. That's very cold. So, so CO2 levels, so let me write down. With zero CO2 level, the average temperature of the Earth would be minus 18 degrees Celsius. Okay. We don't want that. Okay. If you were living on Earth about 200 years ago, the CO2 levels in the atmosphere in parts per million, okay, well, parts per million means for every million molecules of the atmosphere, there were 280 CO2 molecules. With 280 molecules, the average temperature of the Earth was 14 degrees Celsius. And this is good. We want this. And now we are heading towards 450 parts per million. And the temperature is rising. And the temperature, is, like I said, has gone up to 15.3 degrees Celsius, and it's increasing. And this is not good. All right, so maybe if you can wave a magic wand and get the CO2 level back to 280 parts per million, everybody would be happy. Okay, so during the pre-industrial time, around 1800s, level of CO2 of about 220 parts per million, the temperature was a comfortable 14 degrees Celsius. Okay, so you learned that the greenhouse effect is infrared radiation being trapped by the greenhouse gases. Currently, CO2 levels have reached 420 parts per million, and the Earth has warmed to about 15.3 degrees Celsius. Again, our goal is to be below 16 degrees Celsius. I urge you to go visit this site and read up that article. Okay. So again, the concern today is that human activities through fossil fuel consumption and deforestation is increasing greenhouse gases in the atmosphere, leading to the warming of the Earth. Okay, so here's CO2 levels over the last 10,000 years. Okay, so again, see, for the last 10,000, see, this is 10,000 years ago, CO2 levels remain steady below 300 parts per million. And in the last 50, 60 years, the CO2 level has just shot up because we're consuming so much fossil fuels. Okay. And again, currently it's about 420 parts per million. Okay. So that's a 35% increase. So it was steady for 10,000 years. And in the last 60 years, we've increased it by almost 35%. So again, like I said, our goal is to be below 16 degrees Celsius, for the temperature of the Earth to be below 16 degrees Celsius. And these models show you that if the CO2 level concentration is 430 to 480 parts per million, this would be the range of increase in temperature. What this is showing is 2 degree rise in temperature above pre-industrial level. Pre-industrial level was 14 degrees Celsius, and so if the temperature rises by 2 degrees, the temperature of the Earth would be 16 degrees. This would be 17, 18, and so on. And so you see it showing you for various levels of carbon dioxide, the temperature rise. Okay? And again, these are models, so those are the error bars. Okay? So we are almost at the level of CO2 we should have in the atmosphere. Okay? The world needs to switch to renewables as fast as possible. Okay, again, this graph shows you this is the radiation coming, and this is the radiation intensity of the radiation, and this is the wavelength. What we are getting is visible light, and what we are emitting is infrared light. And what this graph is showing you, so this is the graph we're emitting. If our atmosphere had no greenhouse gases, so for instance, if we had no CO2 in the atmosphere and no water vapor, this would be what we would emit to space. But because of CO2 in the atmosphere and water vapor, because of this guy, see, we're only this solid graph is reaching the space. All that heat is being trapped on Earth. Okay. Now, all the heat being trapped, 90% is being absorbed by the oceans. Okay. And that's what this graph is showing you, I guess. So, all right. So let's make sure we understand this phrase, radiative forcing. Radiative forcing is a measure of the energy reaching Earth minus the energy leaving Earth. Okay. So energy reaching Earth minus energy leaving Earth. This is radiative forcing. Yeah. Now, of course, you want this to be zero, okay? And that was zero till the 1800s and so on. Now, there's less leaving than reaching Earth, so this has become positive, and the Earth is warming. Okay, you want this to be zero, but it's become positive. Okay, and I'll show you a graph. Well, how much is it? So this number is about 3.3 watts per meter square. What this means is, for every meter square of the Earth, we are trapping 3.3 joules of energy per second. Watt is joules per second. Okay, so let's go to that table. And I want you guys to closely study this table. Oops. So here's the Wikipedia page on radiative forcing. Okay. I want you to go look at it. So here's the table I want you to study carefully. So we've been keeping track since the 1970s, so late 1970s. So here are the greenhouse gases: carbon dioxide, methane, those are the biggest culprits. Nitrous oxide, CFCs, and HFCs, and so on. Okay. So this is the total amount of energy trapped on Earth. Okay, so this is the how much less energy is being emitted, and this is, like I said, in watts per meter square. Okay, so CO2 out of 1.8 watt per meter square. This is in 1979. Okay, out of 1.8 watt per meter square, carbon dioxide trapped almost 60% of it. Okay, and the next biggest contributor was methane. Okay, and CFCs are also contributing about 10%. So 10% of the heat is being being trapped by the CFCs. Okay. Now let's go to the latest number, the last figures. So in 2022, carbon dioxide trapped 2.2 watts per meter square. The total being trapped was 3.4 watts per meter square. And I'll tell you what that energy means in a second. That's a lot of energy being trapped, and we'll put that in perspective. Okay, so go look at the radiative forcing link. Okay, so there's the link. Okay, so here's, because of human generated greenhouse gases, there's an imbalance of 3.22 watts. Now we saw that the updated figures were 3.4 watts per meter square. The planet is warming as a result. Okay, so go there. So energy is being trapped on Earth at the rate of 1600 times 10 to the 12 watts. Okay, so what that number is telling you is 1.6 into 10 to the power of 15 joules per second is being trapped. What that means is this is equivalent to exploding 20 atom bombs every second and trapping the heat. Every second, 365, 24/7. That's how much heat we're trapping because of the greenhouse gases that we're putting in the atmosphere. Okay, so this is serious. All right, so now what this tells you is how much CO2 there is and so on. So there's as much as 12,000 gigatons of carbon in fossil fuel deposits left today on Earth. Current rate of fossil fuel burning, we're dumping 10 gigatons in the atmosphere every year. 10 gigatons of greenhouse gases. Each gigaton of carbon leads to more or less 3 centimeters, 1 inch of sea level rise in 1,000 years. Okay, so we have dumped 500 gigatons since the Industrial Revolutions. And simulations suggest that another 500 gigatons of carbon end up in the atmosphere, an amount that would require a transition off fossil fuels by the end of this century. So if the world is running 100% on renewables by 2100, we'll still dump another 500 gigatons. Okay. So of course, for future generations' sake, we want to transition to renewables much faster than 2100. Okay. So what will happen if the temperature rises by 2 degrees Celsius? That is, if the global temperature goes from 14 to 16 degrees Celsius. Remember, we are at 15.3 degrees Celsius today. Okay. If this happens, if the temperature rises to 16 degrees Celsius, the irreversible loss of Greenland ice sheet is triggered. Okay, that is, Greenland will completely melt in the next, let's say, Again, this is a rough number in 3 to 10,000 years. And sea levels would rise by about 7 meters. Okay. The associated sea level rise would be, this is a conservative number, 7 to 10 meters. Okay, so about 7 meters, let's say. That would affect, so today about 10% of the world's population, 700 million people, live along coastline that's 10 meters above sea level. And so all these people would be affected. Okay. All those 10% people's home, 10% of the world's population's homes would be underwater if temperature rose to 16 degrees Celsius in a couple of thousand years. Okay. So that's what we're facing. Okay, what are the renewables? What this graph shows is renewables are solar, wind, hydro, and nuclear. Okay, and you'll learn that this won't play a big role, but anyway, solar and wind will play a big role, and hopefully nuclear as well. Okay, so this is what this number says. With the current mix, the world 16 terawatts is 16,000 Hoover dams. So this is how much power you need to run the world. This is how much solar energy is falling on Earth. So you can run the world easily on just solar. You can run the world easily on wind as well. Okay. Now, so, and this shows you geothermal, of course. You can't run the world on geothermal, on hydro, as you can't run on biomass. Okay. But solar and wind today are the cheapest sources of energy, and we could run the world just on solar and wind. The problem with solar and wind is, okay, what do you do at nighttime with solar? Okay, so what you would need is, you would need to charge batteries and then use the batteries to run at nighttime. And the crux of the problem is the batteries are too expensive right now. They're getting cheaper, so once batteries get cheap enough, so if you had cheap batteries, then you could run the world on solar and wind alone. Okay. So again, wave a magic wand and get cheap batteries, and you will solve all problems. Okay. So that's what this shows you. Okay. Okay. Here's another perspective. So if you covered these black dots with solar panels, you could run the world on those solar panels. Okay, alone. Okay. So what you need is at current solar panel efficiencies, which is roughly 20%, 300 kilometers by 300 kilometers, 300 kilometers roughly, okay, it's 200 miles by 200 miles. Okay. You cover this with solar panels, and you can run the world on solar energy. Okay, plus of course you would need cheap batteries. Okay, so that's the limiting technology. Okay. So here's a group in Stanford University that makes the following prediction. Okay, so this is a terawatt is 1,000 gigawatts. Okay, so back in 2012, the world was run on 12,000 gigawatts with 80% fossil fuels and 20% renewables. Okay, well, it was less than renewables. Back then it was probably 90% fossil fuels and 10% renewables. Okay. All right, essentially what this graph says is, by 2050, if you kept the same fossil fuel mixture, okay, the world would need 20,000 Hoover dams to run the world. You would need 20,000 Hoover dams to run the world. But by 2050, if the world is 100% renewable, all you'll need is 12,000 Hoover dams. Okay, and 60% of your energy would be coming from solar, and 40% would be coming from wind. So with renewables, in 2050, instead of 20,000 Hoover dams, all you would need is 12,000 Hoover dams, okay, with renewables. And this is with 80% fossil fuels and 20% renewables. Okay, so we want to get there as fast as possible. That's the goal. All right, so you can see that one of the biggest problems facing mankind is global warming, and the ice sheets are melting. Okay, so my generation has created this problem for your generation to solve. Okay, and I'm sure you will find a solution to the problem. Okay. Anyway, I hope you understood the issue with the fossil fuel use. Okay, and hopefully the world will come up with cheap batteries fast enough where we can switch to renewables as fast as possible. All right, so we'll stop here, and I will post this recording on my YouTube channel.